Now we're going to build our toolbox for integrals. We're going to start with x to the n, right? Learn how to integrate this function. And we're going to use the fact that we know how to take the derivative of x to the n power and basically do the reverse. Before we even do that, though, we're going to start by looking at some rules of integrating a constant. And the nice thing about integrals is it's the area under the curve. So we can put graphs that help us visually understand what these integrals are actually solving for. Okay, so some constant rules. So one rule of integrating constants is, let's say I have a constant C1 and I want to integrate this. This could be equal to 10, or y equals 10, or y equals 4. It doesn't really matter, right? It's a constant that we're integrating across. The integral, the indefinite integral, right? Indefinite meaning there are no set limits, so I'm trying to find a function for this integral, is the constant times x plus a secondary constant. Remember, this constant here is because if I take the derivative of this integrand, then this constant is always going to go to 0. So you have the infinite solutions because you could have infinite values for this constant here. If I take the derivative of c1x, where c1 is a constant, I'll just get c1. So then we know that we took our integral correctly. What does this look like when I have a definite integral? Well, I can have a definite integral, right? So let's say this is my constant y equals 1, and I'm integrating it. The area under this curve is my integral. So I can take the integral from 0 to 1, right? 0 to 1, 1 dx is equal to, well, when you're doing the definite integral, you don't need this extra constant part. Because even if you included it, when you take the upper and lower limits into account, it would drop off, right? It's an offset, so it's gonna drop out. So we just can take into account this term. So it'll be the constant times x. So 1 times x from the lower limit 0 to 1. And so the way we treat these lower and upper limits is we take the integral first. So this is our integrand, right? The function that is our integral, equal to our integral. And we plug in the upper limit first and subtract that by plugging in the lower limit. So I'll plug in the upper limit, I just get 1, and I subtract the lower limit. I plug it in there, I get 0. So 1 minus 0 is 1. And we can double check. This one's very easy because it's just a rectangle. We can double check by looking at the area of this curve, or of this shaded area here, right? 0 to 1, this has a width of 1. 0 to 1, this has a height of 1, so 1 times 1 is just 1, so that's the area here. If I change my integral to go from 0 to 2, 0 to 2, and still have the same function 1x, so all that's changed is my limits. So now if I plug in the upper limit 2, and my lower limit is still 0, so 2 minus 0 is equal to 2. And again, we can check the area in the shaded region, right? So the width here is 2, the height here is 1, 2 times 1 is equal to 2. So that's a very simple constant integral rule, that the integral of a constant is equal to the constant times x. If you put a definite integral, or if not, then you add this extra constant out here for indefinite integrals. The other integral constant rule is if you have an integral of a constant times a function that you know how to you integrate separately, you can pull that constant out, right? So this constant can be pulled out of this integral, and it will be the constant times the integral of that function. Okay, so what does that mean? That means if I want to integrate 2 dx, I can look at this as pulling the constant 2 out of this integral out here, 2 times integral 1 dx. Well, I solved for the integral of 1 dx for the bounds 0 to 2 over here, which was 2. So 2 times that integral 2 is equal to 4. right? And so you can see it visually here as well, right? Width of 2, height of 2, 2 times 2 is 4. I haven't explained how to take the integral of x yet. We'll do that in just a second. But let's assume that we know the integral of x dx from 0 to 1 is 1/2. If I try to show this rule is true, I can have 2x dx, right, with the same bounds. So according to this rule, I could pull the 2 out of this integral, like here, and just say 2 times whatever this integral is. This integral we solved right here as 1/2. So 2 times 1/2 is equal to 1. And again, we can find the area of these triangles and prove that these are true. These two rules are very basic, but get used over and over. And eventually, as you get more comfortable with integrals, you won't even think about applying this rule. It'll just be natural for you to pull the constant out, or just change an integral of a single constant term as the constant times x. All right, so now that we know this rule, we can jump into looking at x to the power n and taking the integral of that, recognizing the derivative rules of x to the n. Okay, so here's the derivative rule that we know. We know the derivative of x to the n is n times x to the n minus 1. And we know that the integral is the reverse of this. So if I say I integrate this function, nx to the n minus 1, then I expect to get my integral to be equal to x to the n, or x to the n plus c, right? I left the constant out there, but that's the idea, is the integral of the derivative term is equal to the original function. I could pull the n out, and I could divide by n on both sides, so the integral of x to the n minus 1 dx with respect to x is equal to x to the n over n, right? And this makes sense because if I take the derivative of this, I get x to the n minus 1 times n, so the n cancels out here, then we get x to the n minus 1. Okay, but let's make this look a little cleaner. It might be nice if I just, like these variables m and n are dummy variables, right? So they're just placeholders. So if I call m n minus 1 and I substitute, now I have integral of x to the m, or x to the n, doesn't matter, right? X to the m in this case is equal to 1 over, this is if this is 1 over n, then 1 over n will be equal to 1 over m plus 1. So 1 over m plus 1 times x to the m plus 1, and then I include the constant c here again, right? So the constant c is up here and here as well. So this is the definition that we will use, right? Again, you can write this as x to the n dx is equal, integral of that is equal to 1 over n plus 1 x to the power n plus 1 plus c. Okay, so how does this look in application? So if I look at m equals 1, or the integral of x dx, this can be 1 over 1 plus 1, right? So I put in green text here where the m term comes from, right? So this is x to the power m, x to the power 1 in this case. So x to the power m plus 1, or 1 plus 1 plus c. So 1/2, right? 1 plus 1, x squared, 1 plus 1 again, plus c. That's the integral of x dx. See if you can figure it out this for m equals 2 and m equals 3. All right, so m equals 2, this is integral of x squared. I get 1 over 2 plus 1, or 1/3, x to 2 plus 1, or x cubed. So x squared, integral of that is 1/3 x cubed. And for m equals 4, or sorry, m equals 3, you get 1/4 x to the 4th. So you see a pattern, right? So very simple, straightforward. We can put different constants in front of this, and that'll just get pulled out in front here. And we could also do this for definite integrals, right? So if I have actual limits, upper and lower limits, I'll get x to the m the integral of this is this first section right here, 1 over n plus 1 x to the n plus 1 at the limits a to b, right? A is my lower limit, b is my upper limit. And all we do is we plug in a and b into my x variable. You plug in the upper limit first, and then you subtract plugging in the lower limit. So I can pull out the constant 1 over n plus 1 times the quantity of x n plus to the power n plus 1 with the upper limit b and lower limit a. So then plug in upper limit b to the power n plus 1 minus the lower limit a to the power n plus 1, right? And this is all we need to do. So we'll take a look at a couple examples where we can look at the graphs, take a look at the indefinite integrals, and then remember, indefinite integrals give us functions and definite integrals give us actual values. Okay, so here we have our definition of indefinite integrals, and this is our formulation for the definite integrals. All right, so let's take a look at here we have 5x. The integral, so the function 5x is shown in black here. The integral of 5x is, you can pull the constant 5 out, and then the integral of x dx is just going to be 1/2 x squared. So 5 times 1/2 x squared plus constant c. And so that's shown in dash red when c is positive 2, it's shown in blue, and when c is negative 2, it's shown in green. Right, just showing that there are infinite solutions to this. Let's set this to a definite integral. So here we have the definite integral from 2 to 5. Take this first part of the integrand and then apply the upper and lower limits 2 to 5. And here's our solution, right? We just literally just plug in. So 5 squared gives us 25, 2 squared gives us 4. So we just subtract the upper limit from the lower limit. And that's this shaded area. So we can also calculate this shaded area, right? If you take the area of this bottom half rectangle and then this triangle up here, if you like. Let's take a look at another example. Here we have 3x squared. Integral of 3x squared, that's 3 times 1 over 2 plus 1, right? So 1 over 3. So the 3 times 1 over 3 cancels out. So we have a constant of 1 times x to the power 2 plus 1, 2 cubed, plus c. So in black, here's my 3x squared. And then here's x cubed plus 2, x cubed minus 2. Right? So it's showing the variations in the dashed lines here. Then we can look at a definite integral. Right? So here again we have our function 3x squared, and then the integral, the definite integral component of this is shaded area under the curve here from -2 to +2, and it gives us +16 by applying the upper and lower limits. And we'll see that depending if the function stays above or below the x-axis, we will have either positive or negative areas. So here, the section that we looked at was all in the y values above x or above 0. So this whole section was a positive area. Similarly here, both on the negative x-axis side and the positive x-axis side, the function is above the x-axis. So the area under the curve both sections are positive. We'll take a look at an example now with an x cubed function where you have area under the curve, and we'll show that it will get a negative value. So here our function is 2x cubed. So the integral of 2x cubed, we have 2 times 3 plus 2 times 1 over 3 plus 1, right? This section there. So we get 2 over 4, or 1/2, times x to the power 3 plus 1, so 4, plus the constant c, right? And so here we have the 2x cubed, and then we have the variations of the x to the fourth terms in the dashed lines. So if we have a definite integral here, we see that we're below the x-axis, so this area is going to be a negative value, as we see right here. And I think we showed this in the previous video, if you have part of the region, let's say I've expanded this region to the positive x-axis, right, the bounds from the somewhere in the negative side to the positive side, we'll have part of it being negative and part of it positive. We'll see that they can cancel each other out and have a integral of equal to 0 or positive or negative depending on what portion. And so we'll look at that from a additive perspective in future videos. But now you know how to take the definite integral of x to the n or x to the m, and we'll get a specific value, specific number. Or if we're looking for a function, we can take the indefinite integral and have a constant c that's floating, right? In this case, if you want to, you can go from 0 to x instead, and then you could define your constant c. So there's a lot of different things we can do with these integrals. So we'll build upon these rules in the next couple of videos, and then we'll look at some applications of when integrals are important in engineering and physics applications.